Hi, it's great to be here. If you have any questions, it's a small enough group, I think you can just interrupt me and I'll try to answer or postpone your question. So this is experiments with 3 approaches to recognizing lexical entailment. This is work I did with my colleague Saif Mohammed. Basically, I'll talk about, introduce the ideas, talk about the algorithms, the data sets, the results, more or less a typical talk, I think. Recognizing textual entailment, probably you all know what that is, but here's a little example from the very first RTE challenge in 2005. There's 2 sentences, a text sentence and a hypothesis sentence, and this is a very simple case. iTunes software has seen strong sales in Europe, is the text, and the hypothesis is strong sales for iTunes in Europe. 2005, these pairs were very simple, but they've grown more and more complicated. Now the text can be an entire paragraph, and the connection between the text and the hypothesis can be difficult to work out. In 2005, the question was simply, does the text entail the hypothesis, yes or no? Later they added things like, does the text contradict the hypothesis? The latest RTE challenges have become fairly challenging and difficult. So why are people interested in this? If you had a black box that could solve these kinds of problems, you feed in a pair of sentences and it pops out a decision, yes, the text entails the hypothesis, or no, it doesn't entail it. You could do a lot of things with that black box. Text summarization, information retrieval, information extraction, question answering, machine translation, paraphrasing. It's a generic task with lots of applications, so many people are very interested in it. Now here's a simple example of a possible RTE question. Text, George was bitten by a dog. Hypothesis, George was attacked by an animal. Now, in order to figure out this entailment between sentences, first you need to figure out the entailment between words. You need to know that bitten entails attacked and dog entails animal. So a good RTE system requires, as a component somewhere, a good recognizing lexical entailment system, an RLE system. And so the focus in this talk is on the problem of RLE, recognizing lexical entailment. And of course, RLE by itself doesn't solve RTE because there's other things, many other things that that are important when you're looking at the sentence level of entailment. But you can't do the best possible RTE without somewhere having some RLE. So what I'm going to talk about is 3 different approaches to recognizing lexical entailment. All 3 use a vector space model of semantics. I imagine you're familiar with that. The basic idea is that words that occur in similar contexts tend to have similar meanings. So given that hypothesis, it's very natural to represent a word as a vector of the context in which it appears. And once you have that kind of vector representation of the word, then use some kind of algorithm to figure out when one vector entails another vector.
Can I ask you a question? Are you going to be more specific about, RT isn't always, well, has a non-operational definition of what it means to have entailment. When you go to the lexical level, are you going to be more crisp about what it means for one lexeme to entail another?
No. It's very, RTE is subjective. It's whether one text entails another is not a formal notion. It's based on just human intuition. Would the average person say, does this sentence entail this sentence? And so with RLE, again, we're just using human intuition. In this case, actually, my intuition and Saif's intuition. So we independently labeled word pairs as entailing or not entailing, and then compared our labels and arrived at a consensus. So, but it's still essentially subjective, and many of the cases could be argued.
Can RLE be solved independently of the text and the hypothesis? Like if you give me two words, they may not entail each other, but in the context of the text and the hypothesis, they do entail. So is it an independent problem, or should it be solved with respect to RTE?
We treat it as independent, and I think it's a reasonable approximation, but they are not entirely independent. So it's kind of a simplifying assumption.
Like even in the first example, bitten and attacked, you need the context to be able to have it.
That's true, but there's some disambiguation happening because you have a pair of words. Bitten by itself might be ambiguous, and attacked by itself might be ambiguous. But when you have bitten and attacked together as a pair, they, to some extent, disambiguate each other. So you know what sense of attacked is being used and what sense of bitten is being used to some degree. So I'm going to talk about three different approaches to deciding whether there's lexical entailment with context vectors. The first is BALAP Inc. This is the oldest approach. This is something that Ido Dagan and his colleagues have been working on for a long time. I'm going to use their 2010 variation of this general approach. The hypothesis behind BALAP Inc. is, I call it the context inclusion hypothesis. So if a word A tends to occur in a subset of the context in which a word B occurs, in other words, B contextually includes A, then A, the narrower term, tends to entail B, the broader term. So the idea is, for example, bitten, the narrower term, entails attacked, the broader term. And hypothetically, the contexts in which you would use the word bitten are a subset of the context in which you would use the word attacked. This idea is basically inspired by formal logic, where you have a subset relation like this in model theory. So the models of A are a subset of the models of B. And the idea of the context inclusion hypothesis is that model subset relations are kind of like context subset relations. It's a questionable hypothesis, but that's the basic idea behind it. The second approach and the third approach take a different view. The second and third approach view this as a relation classification problem. So you have a pair of words A and B, and they have a certain kind of semantic relation between them. And once you know what that relation is, then you can decide whether there's an entailment between A and B. So the second approach, convex, is based on the context combination hypothesis. The tendency of A to entail B is correlated with some learnable function of the context in which A occurs and the context in which B occurs. Some combinations of contexts tend to block entailment, and others tend to allow entailment. And so that hypothesis leads to fairly naturally to the idea of just concatenating the vectors. You have the vector for A and the vector for B, you just concatenate them to make a double-sized vector. And then you apply some kind of machine learning algorithm and treat this as a feature vector and try and figure out what kinds of features involve entailment and which don't involve entailment. So it's a binary classification problem, which is quite a different approach from the hypotheses that are behind BALAP Inc.
Is the first model a special case of this, where they're assuming that function is a subset relationship between the entails?
Yes, you could view it that way, but I don't think Dagan and his colleagues tend to view it that way. And one thing is also this is a supervised learning approach, whereas BALAP Inc. is unsupervised. It's based on using human intuition to hand construct a kind of measure of this subset relation. And the third approach is kind of similar to convex. It's viewing entailment as involving semantic relations in some way, but it doesn't concatenate the vectors. Instead, it uses the similarity differences hypothesis. So the third approach is a new approach that I developed with my colleague Saif Mohammed. It's the idea is the tendency of A to entail B is correlated with some learnable function of the differences in their similarities. The similarity of A to a word R, the relational similarity of a word A to a word R, and this minus the similarity of B to R, where R is some kind of reference word. And some differences tend to block entailment and others tend to allow entailment. And so an example is dog entails animal versus table entails animal. The reference word could be life, and dog and animal are similar with respect to life. So the difference in their similarities with respect to the reference word life is low. When you subtract their similarities, you get a value near 0. But table and life are quite different. So if you compare table and animal using the reference word life, you find a high difference in their similarities to the word life. So you need a set of reference words here that act as kind of benchmarks or reference points in a landscape to tell you where you are. And the idea is that the supervised learning algorithm will figure out which kinds of differences are important, like the animate-inanimate difference may be very important in entailment relations, whereas other differences like the color of a thing may not affect entailment at all.
In this model, are the reference words given as input, or are they discovered?
So they're given as input. What I did is I chose, what Saif and I did is we chose 2,000 words from Basic English. Basic English is an artificial language that was made in the 1930s to teach foreign language speakers to learn English easily. So it's a very reduced subset of English. And so we took, there's different sizes of subsets. There's a 800-word subset, a 2,000-word subset, and then a larger subset, I think of 4,000 words. So we chose the 2,000-word subset of Basic English words. And the idea was if these are core words of English, then they should be a good set of kind of reference points for deciding what entails and what doesn't entail.
Question. How does this take into account the asymmetry of entailment?
If you flip A and B, then the sign of this changes. So you get flipping A and B around, changing their order, changes the signs in the vector you have.
So you're not using cosine, are you?
Yes. Well, no. We're turning it over to a supervised learning algorithm. So each element in this feature vector is a difference of similarity. So R here is 2,000 words from basic. Capital R here is a set of 2,000 words from Basic English. So this is a vector of 2,000 features. And if you flip the order of A and B, you flip the sign of that feature in the vector. So it is sensitive to order. In the test sets, some of the pairs have been flipped around to test to make sure that it responds properly to the order. So bitten entails attacked, but attacked does not entail bitten. So this is just a little comment on semantic relations and lexical entailment. Zitomirsky, Geffet, and Dagan in 2009 spend about a page arguing that entailment does not correspond to classical relations, and so I have to say something about that because I'm saying it does correspond to classical relations. They give some examples of words that for example, part-whole relations. Sometimes a part-whole relation involves entailment and sometimes it doesn't involve entailment. And they argue, therefore, you can't treat the problem of entailment as a problem of classical relations. But a simple way to solve that problem is use a more fine-grained classification of relations. So you have subtypes of the part-whole relation, and some of those subtypes entail and some don't entail. So by moving to a very fine-grained taxonomy of relations, you can address the objection of Zitomirsky, Geffet, and Dagan. And so we use a taxonomy developed by Bedjar, Chaffin, and Embritson. They have a book in 1991 where they look very closely at semantic relations. They work at ETS, the Educational Testing Service, and they were studying analogy questions for the GRE test. And in analyzing how those questions are formed, they came up with this taxonomy of 79 different types of semantic relations.
Peter, I'm sorry to interrupt, but I'm confused by something here. The distinction that you guys are computing, right, is, you know, lexical entailment or not. And here you're saying there's these 79 subcategories, which sounds fascinating, but I don't understand. Maybe that's coming next.
I think I'll just step outside of this for a second. I'm going to go to the journal paper because there's a table that I think will help explain this. Oh.
By the way, note to the team, if you're giving a talk and you're asked a question like this, if you can just go to the journal paper, that often really helps to settle any...
So this is part of the table that lists the 79 different semantic relations. They're arranged in, there's 10 high-level categories. So the numbers 1 here are all class inclusion relation. And then these are, within the high-level category, there are these more fine-grained relations. And so this table has examples of each of these. So here are the part-whole relations, and there's, I think, 10 types of part-whole relations. And what we have in this table is, given this pair AB, does A entail B? And 0 means no, A does not entail B, and 1 means yes. So there's, and we look at both orders, A entail B and B entail A. So most things only go in one direction. So Everest entails mountain, but mountain does not entail Everest. But there's a couple that are bidirectional. For example, car and auto entail in both directions. And then there's some where there's no entailment in either direction. So Saif and I went through the 79 relations and independently labeled them with these 0s and 1s, and then came to a consensus on which cases entail and which don't. And I think you can argue with each of these, but we were able to come to agreement. So it involves intuition, and these are all kind of fuzzy, and you could say there are contexts in which they don't apply, but we feel that in most cases it's fairly clear. Like if you've got a glacier, then you've got some ice.
I guess the question I'm trying to ask is a little bit fuzzy, I apologize, but it seems like you defined a task, lexical entailment, and you define it by reference to intersubjective agreement, and then you can measure performance on that, and life is good. So I guess the more succinct version of my question, which I don't mean, but is like, who cares about this part? So I don't understand why we should care about this in the way you framed the task.
I think what you're saying is there's two ways we could have evaluated our success on this task. One is by seeing whether our system can match these human labels on words, and another is by embedding it inside an RTE system and seeing whether it improves the performance of the RTE system. And if we'd taken the second approach, I think that would have made you happier. Is that right?
You know what, I'm taking this too far afield. We'll talk afterwards.
Okay.
I apologize.
No problem. So there's three approaches here: BALOP, Inc., Convex, and SimDiffs. The first one is based on asymmetric similarity measures for context vectors, and the second and third are based on the work in supervised learning of semantic relations. And this is something that's been going on. Both of these have been going on for quite some time, and there's a lot of papers in both areas. But there's actually very little that looks at the overlap of the two areas, which is what I'm doing here. And I could only find 2 papers that actually looked at the overlap of lexical entailment and semantic relations, which I think is a little bit surprising, because it seems very intuitive to me to think that behind every kind of lexical entailment there must be some kind of relation that explains the entailment. I think people tend to assume that that relation is either a part-whole relation or a hyponym-hypernym relation. Most papers that you see on lexical entailment tend to make that assumption, and I think when you look at the taxonomy of 79 relations that Bejar and Chaffin have made, you can see that there's a lot of other kinds of relations that have some sort of entailment going on in them. Now, performance measures, these 2 different approaches, the unsupervised BALOP Inc. and the supervised Convex and SimDiffs, are doing different things. BALOP Inc. Generates a real-valued score, whereas supervised learning is a binary classification. But so it might look like you can't compare these 2 approaches, but it's actually not that difficult to compare them, because, for example, with BALOP Inc., the real valued score, you can turn it into binary just by putting a threshold on it. And for supervised learning, there are a lot of supervised learning systems, including the ones that we use here, that can take a binary classification and convert it to a real valued probability estimate that tells you the probability of being in one class or the other. So we use 2 types of performance measures. The first type is the traditional way that Dagan and his colleagues have been using, which is adapted to dealing with a real valued score. It uses average precision to decide whether that real valued score is a good score. The second group of scores are precision, recall, F measure, and accuracy. Assume you have a binary score. So we analyze the results from those 2 different perspectives. So BALOP Inc. is based on the context inclusion hypothesis and generates a real-valued similarity measure that's sensitive to the order of the pair AB. These are the equations that define BALOP Inc., and I don't intend to go through them and explain them to you. I just wanted to give you a sense of how complicated BALOP Inc. is. It's not an intuitive thing. The idea, the hypothesis behind it seems pretty intuitive, one context including another, but the equations are actually quite complicated. And these have evolved over the years. Dagan and his colleagues started working on this in 2005, and so this is a 2010 paper, and the equations get more and more complicated, which is one advantage of moving to a supervised learning approach. You let the learner figure out these kinds of things. You don't have to hand code complicated equations. You just have to figure out what the right features are. So convex, the right features are just concatenating your vectors, and that gives you the features you need, your context vectors. And once you've got them concatenated, then you turn it over to a supervised learning algorithm that tries to figure out which features are important and how to combine them to decide whether a particular pair of words should be classified as entailing or not entailing. So this is work that Marco Baroni did with some colleagues, and they used a support vector machine as their supervised learning system. And there's a support vector machine in Weka that will give you probability estimates for the classes. So that's what we used in the experiments here. SimDiffs, again, we used a support vector machine. It's supervised learning binary classification. These are what the features look like. We actually have 4 different types of features. So I mentioned before there's 2,000 words in basic English. Because we use 4 different types of features, there's actually 8,000 features in the vectors. SimF is function similarity, and SimD is domain similarity. This relates to a paper I did in 2012 on 2 types of similarity. Domain similarity is topic similarity. It's like animal and dog are from the same domain, the domain of living creatures. Animal and table are from different domains. One's the domain of living creatures, the other's the domain of furniture. So domain similarity captures that difference between the topic or domain of words. Function similarity is about how a word is used in a sentence. It's about how it relates to the neighboring verbs. So functional similarity, for example, captures part of speech in the sense that words that are in the same part of speech will have a higher degree of functional similarity than words that are in different parts of speech. It captures other kinds of similarity, like cut and carve are similar functions. They're similar actions, and they tend to be used in similar ways in sentences. Cut and bill, or well, cut and hammer, say, they're different kinds of actions. So even though they're both verbs, they won't have quite the same degree of functional similarity as cut and carve. We use 3 data sets. Each of these data sets was created by the people who created the different algorithms. So this data set, in a way, is the best. The KDSZ data set was designed for the BALAP Inc. algorithm, or the BALAP Inc. algorithm was kind of tuned to it. So it's the ideal set for the BALAP Inc. algorithm. The pairs in this data set, the word pairs, were labeled entails or does not entail by 3 judges, and they had quite a high degree of agreement. They define entails as a kind of substitutability thing. So in a sense, they asked the judges to imagine, for example, in the case of dog and animal, imagine a sentence that contains dog. Can you substitute animal in the place of dog in that sentence? And if you can, then it should be labeled entailed. If you can't, then it should be labeled does not entail. So this definition of entailment is subjective, but it leads to fairly high levels of agreement. But a problem with it is I think, too strict a definition, because you could say that do I have an example? You can get entailment between words that are different parts of speech. But words that are different parts of speech can't be substituted for each other. So by using the substitutability definition of entailment, they eliminate a lot of cases where people would say there really is some kind of entailment. The BBDS data set was developed by Baroni and his colleagues, and almost all of the pairs in this set are hyponym-hypernym pairs. So they approach entailment as a relation classification problem, but their focus is really on hyponym-hypernym relations. They don't consider all the other possible relations that a word pair can have. The third data set is based on a data set of Jurgen, Mohammed, Turney, and Holyoke. We developed this data set for the 2012 Semival. It's a semantic relation classification data set. We had Turkers generate word pairs and label them using Bejar's taxonomy of 79 relation classes. So this is, of the three data sets, this is the only one that spans a very wide variety of semantic relations. The Baroni data set is almost all hyponym-hypernym, and the Kotlerman data set is a mix of hypernym-hyponym and part-whole meronym relations. So they span a much narrower range of semantic relations. So now we do three sets of, yes?
In your first data set, is that are people labeling things as 0-1 binary? Dogs, entails, animals, although I cannot substitute all the time, they will call it a 1.
The KDSZ data set, yes, it's binary. And
so many statements about dogs, that you take dogs on a walk and they are small, they are furry, they don't apply to all animals, so people would mark it as a yes typically? Or?
The instructions to the annotators say, if you can imagine some kind of sentence where there's entailment, then label it as entailed. So if the dog-animal thing, you can imagine sentences where they don't entail, but the important thing is you can imagine sentences where they do entail. That's the instructions they give to the annotators.
In your mapping to 79 classes, how much inter-annotator agreements do you get?
About 80%. So there's a drop from the 90% that they got in the Kotlerman data set, because we're using a broader definition. The instructions for their annotators were substitutability. We don't use substitutability, we use semantic relations. We say, if it's this relation, then the table I showed earlier shows that there's entailment in that relation. So by going to relations as a foundation for lexical entailment instead of substitutability, we allow relations across parts of speech. We double the number of pairs that get labeled as having entailment. But we get, in effect, double the recall, but the precision drops from 90 down to 80. So it's a kind of precision recall trade-off. So with the JMTH data set, this is the one that has the 79 pairs of relations. Actually multiply that by 2 because the relations can be in either order. So it's 79 times 2 classes. We split the data set into 3 parts, 2 development parts for tuning parameters and 1 test part. And these are the results. For all of the performance measures, average precision, recall, F measure, accuracy, there's the same basic pattern. The convex and SimDiffs give quite close results. The difference is not significant. So convex gets 70.2% and SimDiffs get 72.4%. The difference is not significant. But Balap Inc. Is way behind the other two. And this is mainly because this data set spans a huge variety of relations. And Balap Inc. was really intended for hyponym, hypernym, and meronym relations. So it really has problems with the other kinds of relations. So the hypothesis behind Balap Inc. of context inclusion doesn't apply to a lot of the other kinds of relations.
Question? So this is, again, for a binary classification task. It's not for predicting the actual 79 subclasses, yes?
That's right. The 79 times 2 classes are merged into just binary using the table that I showed earlier. So those zeros and ones in the columns tell you how to merge those 158 classes into just 2 classes.
And the 80% inner-annotator agreement is also for the binary classification?
Yeah. Yeah, we don't, you could approach this by first trying to recognize which relation is involved and then mapping that relation into a decision of does it entail or does it not entail. But we haven't tested this, but our hypothesis is that it's easier for the supervised learner if you just convert it all directly to binary and let it work with binary, because supervised learners tend to have problems when you have 158 different classes you're trying to classify. I think I'll skip over that. So this is moving on to the second data set, the KDSZ data set. This is the Kotlerman data set. There's some problems with this data set. There are many, every word pair in the data set is unique, but there are many pairs that share a word. And so if you train it using supervised learning, it may, when you test it, it may not have seen, it will not have seen the testing pair before, but it may have seen pairs that share a word with that testing pair many times in the training set. So if you just do a standard tenfold cross-validation, it's going to be a little bit problematic because you're really giving it the algorithm a big hint due to this overlap in the pairs. So we tried the standard tenfold cross-validation, but we also tried a clustered cross-validation where pairs that shared a word were put into the same fold, which adds an extra degree of challenge. And furthermore, the data set wasn't balanced. There were a lot more non-entailing relations than entailing. So we tried balancing the data set. And the fourth scenario, which is even a higher degree of challenge, is training the learning systems on the JMTH data set and then using that model from the JMTH data set to guess the entailment relations in the Kotlerman data set. So I think the most realistic situation is what we call the different situation, where you're trained on a completely different data set and then you test on the Kotlerman data set. Because in a real world scenario, you're going to train your system on whatever data you have to build your system, and then you're going to turn it over to someone to use for some practical application. And the data that they're going to be feeding through it may be completely different from the kinds of pairs that you have in your training data. So when you look at the most realistic scenario, there's no significant difference between the three approaches. They all do just about the same on this data set, which, as I said, is a mix of mironyms and hyponym hypernyms. The final data set is the Baroni data set, which is entirely hyponym hypernym relations. And again, there's this issue of shared words. Every pair is unique, but there are a lot of pairs that share a word. So we did the standard tenfold cross-validation and a clustered cross-validation, and also the different scenario where the training data set is completely different from the testing data set. And in this case, SimDiffs is significantly better than the other two algorithms. And here's a summary of the three experiments. So the bold numbers mark the cases where an algorithm is significantly worse than SimDiffs. And there are no cases where an algorithm is significantly better. So there's two cases where SimDiffs beats the other algorithms for the BBDDS data set, and one case where it beats BALAP Inc. You like that? So, summarizing the results, I didn't get the first point. I'll just skip over it. Manually designing asymmetric similarity measures is quite challenging. You remember those equations I showed you for BALAP Inc. There's a lot of difficult thinking went into creating those equations. When you switch to a supervised approach, as Baroni did and as Saif and I did, all you have to design is the features for your feature vector, and you let the supervised learner worry about what to do with those features. And it's a whole lot easier to design features than it is to design the equations behind BALAP Inc. So future work, this is building on, I think, but I'm not sure if I understood your comment, that this is kind of an intrinsic evaluation that we've done, a direct evaluation of the various algorithms. But what you really want to know is RLE, recognizing lexical entailment, does not stand on its own. It's only useful as a module in a larger system, a recognizing textual entailment system. And what you really want to know is, does it help in a module? And we don't know that. We haven't done that experiment yet. But Dagan and his colleagues have done the experiment with BALAP Inc., and they did find that BALAP Inc. improved the performance of a RTE system by about 1%, but it was statistically significant. So hopefully the results here, which show that SimDiffs is working better than BALAP Inc., promise that if you use SimDiffs in your RTE system, you'll get a more than 1% improvement on RTE. A lot of past work has focused on the context inclusion hypothesis, and one of the important lessons we think this work shows is thinking of entailment, lexical entailment, as a property of semantic relations is a fruitful way to go for future research, instead of thinking it as a context subset thing. Final slide. Thanks for your patience. SimDiffs is better than BALAP Inc. and convex. Supervised learning is better than manual building of asymmetric similarity measures. And we think there's a strong connection between lexical entailment and semantic relations, and it's a good idea to bring together these two research areas which have been almost entirely independent so far. Thank you.